Hello, and welcome back, everybody. In geometry today, we will be looking at similarity. What does the word mean, and how does that apply to geometry? You might have heard a word before. Another word that we use for it is proportional, and we're going to go ahead and connect those dots from algebra to geometry for that terminology. Then, okay. So let's go ahead and get started, and I'm going to erase this thing on the right-hand side for you. So first of all, we're going to go ahead and, like I said, define the term similar in geometry. What does it actually mean then? When it comes to basic math, we know the following is true. If you have 1/2, that's definitely equal to 2/4, which is equal to 3/6, which is equal to 4/8. So in terms of how we define similarity, we basically look at that equation right there and say the following then. We would say that the numerators 1, 2, 3, 4, and that sequence of numbers in the numerator is then similar to the sequence of number that's in the corresponding denominator 2, 4, 6, 8, and so forth. So that's what similarity means. So if you look at the two sequence of numbers, you can basically take one sequence, the 1, 2, 3, 4, and so on, multiply by 2, and then you would get the other sequence. So 2, 4, 6, 8, and so forth. So the way that we would write similarity is that we can just say that they are similar like this, or we can use this little squiggly line symbol to indicate that they are similar to each other. So let's go ahead and take a look at an example over here of similarity then. So if you have, like, say, a fraction set up such that 5/7 is equal to 10 over 14, which is equal to 15 over 21, which is equal to 20 over 28, and there are definitely a lot more fractions that we can set up for this. We can go ahead and conclude the following then. 5, comma 10, comma 15, comma 20, the sequence of numbers that are on the top are going to be similar to the sequence of numbers on the bottom that corresponds to it. So 7, 14, 21, and 28, and so on and so on and so on. So if you notice, the left-hand side is really just kind of like saying we have a bunch of multiples of 5, and then on the right we have a bunch of multiples of 7. If we divide the sequence on the left by 5, we would get 1, 2, 3, 4, 5, and so forth. And whereas if we divide 7 on the right-hand side, we would also get 1, 2, 3, 4, 5, 6, 7, and so forth then, okay? So that is the term that is the definition of similarity when it comes to algebra, and also, all the basic math before that. Now, here, when we look at similarity, we're looking at a sequence of number. And when it comes to that, then that means that the thing that we defined earlier in the beginning of the semester, the first semester, also holds true. Similarity with sequences is an equivalence relation. Now, if you don't remember what equivalence relation means, that means that it follows or it satisfies the following, the following properties. There's the reflexive property, which says that if you have a sequence of number, that should be similar to itself. There is the symmetric property, which says that if you have one sequence and it's similar to another sequence, then the second sequence is similar to the first sequence. And finally, for the transitive property, which says that if sequence 1 is similar to sequence 2, and sequence 2 is similar to sequence 3, then sequence 1 is similar then to sequence 3 then. So those three properties will actually be true because of equivalence relation. So let's go ahead and hold that for the time being, and we're going to come back to it, and you'll see why that's going to link up in geometry. Now, in between, what we're going to do is we're going to do kind of like a small little numerical exercise to kind of help you out with this similarity thing. Now, in algebra, we define something that's called an arithmetic mean as the average of two numbers. Now, if you've never heard of the term arithmetic mean, that just means average, or maybe just plain old mean, for example. So here, if I'm trying to find the arithmetic mean, that's what AM stands for, between 10 and 20, well, that number, according to algebra, is going to be 15. And the reason for that is, well, how do you find the average between two numbers? We take the two numbers, we add it together, and then divide by 2. So that's where the 15 comes from. And if we look at it as a sequence, you can see that 10 and then 15 and then 20 over here would then be the middle number that satisfies this. Now, again, if we look at this as a sequence, the pattern over here between 10 to 15 to 20 is that we consistently add 5 in order to get one term for the other. So that's what it means by arithmetic mean, because we're going to add consistently in order to get from one term to another. So that numerical value that we're adding in this case is going to be 5 in order to get to the middle, then into the end. So for example, maybe if I have, like, say, just giving another example, let's say that we have the number 7, and then we also have the number 17. In order to find the number in between that acts as an arithmetic mean, we'll do exactly the same thing. 17 plus 7 divided by 2, which is going to be equal to 24 divided by 2, so the answer is equal to 12. So that is going to be my arithmetic mean then. So in this case, I'm adding consistently once again by 5, and it doesn't always have to be added by 5, just make sure that it's consistently adding by the same number in order to get one from the other. So that's the arithmetic mean then. Now, for geometric, or for geometry, there is something that's a little bit new then. So here in geometry, we're going to define what is a geometric mean. Now, a geometric mean is kind of the same idea. It's also the average of two numbers, but not in the same manner as you would think. So here's what I mean by geometric mean. In the arithmetic mean, as we said, we are adding consistently in order to get from the first number to that arithmetic mean in order to get to the last number. In the geometric mean, what we're doing is we're setting up a sequence that's kind of the same thing. But instead, we're going to want the following. We want a number between 9 and 36 where you multiply by something consistently in order to get to the middle number. And then we multiply something again consistently in order to get to the last number. So that is to say we need to multiply by something to get to the middle number. And then we need to multiply again by another something, which is the same number, in order to get to the last number. Well, to kind of save you a little bit of time, this number, the geometric mean in this case, is going to be 18, and I'll show you how to get that in just a sec. And the reason why it's 18, well, because over here, if I take 9 times 2, you can see that gets to 18. And if I take 18 times 2, that will give me to 36. So hence, that's why this is going to be my geometric mean then. Now, the question then is, well, how do you get that 18, which is the geometric mean in this case? And this is where all those sequencing thing comes in handy. Because here's how you're going to set it up. If I take, let's see, 9 multiplied by some number, which we're going to go ahead and call r, is going to be equal to the geometric mean. Okay, and then if we take that middle number, which again is going to be our geometric mean times r, that will get us to the 36. Focus over here. I want to solve for either the geometric mean or solve for the r. So that means I need to solve for one of those two variables. So we'll go ahead and do a little bit of a substitution, just so then that way we can see how this actually works out. So if I were to make a substitution, let's go ahead and take this first equation over here and solve for gm. So actually, we don't have to do that. GM is already isolated. Let me go ahead and take that and plug it into the second equation. Okay, if GM is equal to 9 times R, then that means that this gets replaced by 9 times R, which is equal to 36. See, GM is right here is equal to 9 times R. So now what I'm going to do is we need to solve for R, so we need to get it all by itself. So then that means we have r squared is equal to 36 divided by 9. And then that would be given, that will give us 4 because 36 divided by 9 is equal to 4. So r in this case is equal to 2. Now technically it's plus or minus 2, but we'll stay away from the negative realm for the time being. But there you go. You found out what r is, which is the ratio or the number that you multiply in order to get from one term to the next. So that will allow you to take your 9, multiply by 2. That's how we get to 18. And then we multiply by 2 again, and that will again get us to the 36. Now, if all of that is kind of like, a lot, really, really wordy, let's kind of simplify this a little bit just so that you can see what happens then, okay? So if I were to, let's say, take this example and I want to set it up as kind of like an equation, so then that way I can like plug it in to solve for it. Let's go ahead and take that middle piece, which says 9 times r is equal to 36. What I'm going to do is I'm going to go ahead and divide r from both sides. So then that way we have the following. We have 9 divided by r is, oh, sorry, messed it up over there. We have 9 times r because we got rid of one of the r, okay? So 9 times r is equal to 36 divided by r, okay? And can we actually do something else to this? Let's see. I want to say that we can. No, I think darn it. I really want to. I am at a loss of word. Here, actually, you know what? Let's do it this way then. I think this might be a little bit better. Okay. Remember, I want to solve for r. So what I'll do is I'm going to go ahead and, oh, you know what? Here, I think this is actually better right here. Let's go ahead and use this guy over here. Okay. R squared is equal to 36 divided by 9. Okay. R squared is equal to 36 divided by 9. That right there shows you the last number and also the initial number. And that's how you're going to solve for r because it's equal to r squared. Okay, so here, let me kind of give you like another example. So then that way you can know how to solve for the geometric mean then. So let's say this time we have the number 6. And also, I want to go ahead and find that and the geometric mean between 6 and 54. In fact, I think I did that. That's going to be my example in a little bit, but you know, it's okay. We're going to go ahead and spoil it right now. Let's say I want to find the geometric mean, okay, between 6 and 54. So that means I need to find a number in between that is going to act as kind of quote unquote my middle so I can multiply consistently. So first, what that means is we're going to go ahead and say that r is the number that I'm going to multiply in order to get from 6 to get to the middle. And if I multiply r again from that middle number, that will get me to 54. Well, according to this, I guess kind of like, you know, quasi formula that I came up with, we can say that r squared is equal to 54 divided by 6, right? Because if you notice earlier, right, r squared is equal to 36 divided by 9, where 36 is the last number and 9 is going to be the first number. So in this case, if we clean up our equation right here, then r squared is equal to 54 divided by 6, which is equal to 9. Then r is equal to 3. So then that means that if I take my 6 and multiply it by 3, then that would give me my middle number, which in this case is going to be 18. And then if you notice, if I take that 18 and multiply by 3, then that would get me to the 54. Okay, so that's how you find the geometric mean. Now, if you're wondering, okay, well, this is kind of like very far on the left field because this seems kind of irrelevant to what we've been doing so far, it'll come into play in about a few sections. So you'll see why this is going to be introduced, okay? So that's the idea for right now, okay? So that's going to be how we define the geometric mean. So there it is. I just kind of did this example for you. Find the arithmetic mean between 6 and 54. Well, we already did it for geometric mean. We said that the geometric mean is supposed to be equal to 18 in this case, right? So that is going to be my GM. And if you want to find the arithmetic mean, well, that's just going back to your basic math. So we can go ahead and say 6 plus 54 divided by 2 because we have two numbers. So let's see, that's going to be 60 divided by 2. So the average is going to be 30 then. So 6 comma 30 comma 54, you can see that over here, you are adding by 24 consistently in order to get from one number to the next. But whereas for the 18 over here, right, you have 6 comma 18 comma 54. In this case, the geometric mean, you are consistently multiplying by 3 in order to get from the 6 to the 18 and then to the from the 18 to the 54. Okay. All right. So now the last thing I want to define for you is a proportionality or similarity between triangles. So, you know, taking everything that we learned so far in geometry about triangles, how does the word similar apply to triangles? Well, we're going to define it by the following. Two triangles, ABC and DEF, are similar, and the way that we can denote it is ABC and then the squiggly line and then DEF, so that's basically the same thing, means the following. So here you can see my two triangles right here. If the two triangles are similar, then that means that the length of AB divided by the length of DE should be equal to the length of AC divided by the length of DE or DF. And then BC right here would then be divided by EF right here, and that's going to equal to the same proportionality. So what that means is side to side, they still correspond, but they are not equal to each other like congruency, but instead they are going to be some sort of proportionality. Let me show you numerically as to what I'm saying. So over here, if I have, like, say, a number set up such that it's going to be, oh, sorry, messed up right here. Okay. Let's say that numerically, if I have a triangle that's 3, 4, and 5 over here, and then we have another triangle over here on the right-hand side that is going to be 30, 40, and 50, we can say that these two triangles are similar to each other. Because if you look at the proportionality that I can set up, we can say that 3 over 30 is equal to 4 over 40, which is equal to 5 over 50. So you can see how AB still corresponds to DE. We can have AC still corresponds to DF. And then finally, BC over here still corresponds to EF. Note once again that the lengths are not equal to each other because we're not dealing with congruency, but instead we're dealing with a proportionality. Okay, so you can see that proportionality set up right there. Okay, so that is our definition of similar for two triangles then. Okay. All right, so we will discover a little bit more about this in this entire chapter. And one thing you probably noticed already, but we're going to go ahead and write that as a theorem in the near future, is that when two triangles are similar to each other, you'll notice that their angles are all congruent. So that is to say, angle A is congruent to angle D. Angle B is congruent to angle E. And finally, angle C is congruent to angle F. Okay, so if you remember, the only one that we did not look at, or actually one of those situations that we looked at that does not show congruency in triangle is AAA. Because in this case, you can see that two triangles are similar to each other if all angles are congruent and nothing else. All right, so we'll go ahead and put an end to it. Thank you so much for watching. I will see you guys next time. Okay, goodbye.